Welcome to True Projects. In this video, we are going to explain about the project entitled as EffNet SVM, a hybrid model for diabetic retinopathy classification using retinal fundus images. So before getting into the video, let me give you the brief description about the project. The project focuses on detecting and classifying diabetic retinopathy, a diabetes related eye disease from retinal images. It combines EffNet, a deep learning model for extracting high quality image features, with SVM, a machine learning classifier, to improve accuracy and efficiency. This hybrid approach leverages the strengths of both deep feature extraction and robust classification for precise diagnosis. Coming to the abstract, the diabetic retinopathy is a serious eye condition caused by diabetes that can result in vision loss if it is not detected or treated early. Detecting diabetic retinopathy in its early stage is critical, and retinal fundus images provide a non invasive way to examine the retina for signs of the disease. However, traditional detection methods depends on manual analysis by ophthalmologists, which can be time consuming, subjective, and prone to human error. To address these challenges, this project introduces a hybrid model that combines EffNet, a powerful convolutional neural network capable of automatically extracting detailed features from retinal images, with a support vector machine classifier which excels at distinguish between different classes. By integrating EffNet deep feature extraction with SVM's precise classification ability, the proposed approach enhances the accuracy and reliability of diabetic retinopathy detection. This method can automatically classify retinal images into various stages of diabetic retinopathy, providing an efficient, consistent, and potential life saving tool for early diagnosis and treatment planning. Coming to the existing system, in existing systems, diabetic retinopathy detection largely depends on traditional image processing and convolutional machine learning methods. Typically, these approaches involve manual extracting features from retinal fundus images such as texture patterns, blood vessel structures, or lesions, and then feeding them into classifiers like k-nearest neighbor or simple neural networks. While these methods can detect diabetic retinopathy, they come with several drawbacks. Manual feature extraction requires deep domain expertise and it's time consuming, making it difficult to scale. Additionally, these systems can often computationally intense and tend to have lower accuracy, particularly when identifying early stage of diabetic retinopathy. Beyond algorithmic limitations, many screenings still rely on manual examinations by ophthalmologists, which is subjective, labor intensive, and inefficient for analyzing large volumes of retinal images. As a result, these existing methods are less reliable and less but practical for early and large scale diabetic retinopathy detection. Coming to the proposed system or base paper work, the proposed system presents a hybrid deep learning approach that integrates efficient net with a support vector machine to enhance the detection and classification of diabetic retinopathy from retinal fundus images. In this system, efficient net automatically extracts high level discriminative features from the images, eliminating the need for manual feature engineering and capturing subtle patterns that may indicate early stage of diabetic retinopathy. These extracted features are then passed to an SVM classifier which excels to accurately distinguish between different severity levels of diabetic retinopathy, providing precise and robust classification. By combining the features extraction, power of efficient net with the classification strength of SVM, the model is capable of handling large dataset efficiently and achieving higher accuracy than traditional methods. This hybrid approach not only automates the diagnosis process but also supports ophthalmologists by offering a fast, reliable, and scalable tool for early detection of screening of diabetic retinopathy. Coming to the data set, the APTOS 2019 JPJ dataset is publicly available collection of retinal fundus images specifically curated for research on diabetic retinopathy detection and grading. It consists thousands of high-resolution color photographs of the retina captured under varying image conditions that reflect real-world clinical scenarios. Each image is manually labeled by clinicians with DR severity score on a 5-level scale ranging 0 to 4. The dataset indicates images of different resolutions and quality, making it suitable for training and evaluating machine learning models that aims to automatically classify DR severity. Originally released as per Originally released as part of the Kaggle Buildness Detection Challenge, the dataset enables the development of automated diagnostic systems with performance commonly evaluated using metrics like quadric weighted kappa to measure agreement with expert annotations. Coming to the novelty or extinction or enhancement or improvement. As an extension to main approach, additional deep learning architectures such as Exception and NASNet Mobile were applied for analyzing the retinal images. Ensemble methods, which combine two or more models, were also used to improve prediction accuracy. A voting classifier was implemented to aggregate predictions for multiple models, leveraging their strengths and reducing the risk of individual model errors. Additionally, models from YOLO family were utilized to detect specific diabetic symptoms in retinal images such as lesion or hemorrhages. Furthermore, to make the model prediction more interpretable, GradCam was employed. This technique generates heat maps that highlight the regions of retinal image that contributed most of the model's decision, helping clinicians understand why a particular classification was made. And to make the system accessible for practical use, a Flask based web interface was developed. This UI allows users to input retinal fundus images and receive predictions from the trained models, enabling a simple and interactive way to test the models without needing programming knowledge. Coming to the flow of the work, first, we need to import the packages. The workflow begins by importing all required Python libraries and frameworks necessary for image processing, deep learning, machine learning, and web development. This includes libraries such as PyTorch and Torch Vision for deep learning, Pillow and OpenCV for image handling, Scikit-learn for traditional machine learning models, YOLO frameworks for object detection, and Flask for building web interface. Proper environment setup ensures smooth execution of training, evaluation, and interference pipelines. Next, data preparation. The APTOS 2019 JPG dataset is downloaded from Kaggle and used as the primary data source for diabetic retinopathy analysis. Unnecessary files such as details.txt are manually removed to maintain a clean dataset structure. The dataset is organized to support both classification and detection tasks, ensuring that images are corresponding labels are correctly mapped for efficient training and evaluation. Next, pre-processing. Pre-processing is performed separately for classification and detection tasks. For classification, traditional machine learning pre-processing involves reading images using Pillow, resizing them to 128 into 128 pixel, extracting HOG features and scaling the data. Deep learning based pre-processing includes image data augmentation techniques such as resizing image of 299 into 292, applying random horizontal flips and rotation, and converting messages into TensorFlow format using torch vision transformers. EffNet is then used to extract high-level features with images, reshaping appropriately using unsqueeze operations. For detection, multiple datasets are merged into a unified dataset and a data.yaml file is created to define image, paths, and class labels required for YOLO training. Next, maintaining parallel datasets. To support both classification and detection simultaneously, parallel datasets are maintained. The classification dataset contains retinal images paired with their corresponding DR severity labels, with the YOLO dataset consists of images along with bounding box annotations that localize diabetic abnormalities. Maintaining separate yet synchronized dataset allows the system to efficiently handle both prediction tasks without data conflicts. Next, model training. Model training is carried out using a five-fold cross-validation strategy to improve robustness and generalization. Baseline classification models such as ResNet 50, MobileNet V2, and DenseNet 121 are first trained and evaluated. The proposed hybrid models, including modified EffNet V2, SVM with a RBF kernel, and an EffNet SVM combination, and then trained to enhance classification performance. Extinction models such as exception, NASNet large, ensemble voting classifiers, and hybrid ensemble approaches are also implemented to further boost accuracy. For detection, multiple YOLO versions are trained with each model training both the local location and type of diabetic abnormalities. Next, model evaluation. The trained models are evaluated using appropriate performance metrics. Classification models are assessed using accuracy, precision, recall, FN score, and confusion matrix to measure predictive performance across DR severity levels. Next, YOLO based detection models are evaluated using mean average precision, and recall. Comparative analysis across different models and YOLO versions is conducted to identify the most effective approach for diabetic retinopathy detection and classification. Next, interface pipeline. The final module focuses on deployment and user interaction through a Flask-based web application. Users can upload Retinal Fundus images via simple HTML frontend on the backend. The uploaded image is first processed by the YOLO model to detect the localized abnormalities using bounding boxes. The detected regions are then passed to the classification ensemble to predict the diabetic retinopathy severity. The output is displayed to the user as an annotated images with bounding boxes, predicted class labels, and confidence scores, providing a fast, reliable, and user-friendly diagnostic support system. The algorithms used are baseline models ResNet 50, MobileNet V2, DenseNet 121. Proposed models are SVM with RBF, modified EffNet V2, EffNet plus SVM. As an extension, we have used Ensemble Voting Classifier, which combines XGBoost plus Light GBM, and EffNet V2 plus Ensemble, that is voting classifier, and Exception NASNet Large, and Ensemble model, which consists of Exception plus NASNet. For extension YOLO-based detection models, we have used YOLO V5, YOLO V8, YOLO V9, and YOLO V11. Coming to the requirements, we have both hardware requirements and software requirements. Hardware requirements consisting of operating systems Windows only, processor i5 and above, RAM 8 GB and above, hard disk 25 GB and above. Software requirements consisting of application framework is Anaconda, primary language is Python, front-end framework is Flask, backend is Jupyter Notebook, database is SQLite 3. Technologies which we use to build the front-end are HTML, CSS, JavaScript, and Bootstrap 4. To execute the project, first we need to open the code folder which contains the project source code files. This folder is a complete package of your project's code base containing everything needed to develop, test, and deploy your application or model. Static folder. This folder consists of files related to CSS, JavaScript, and Bootstrap. Templates folder. This folder consists of all the HTML pages used in the project. It typically includes files like index.html, about.html, etc., which represents different pages of the website. App.py file. This .py file contains the information related to front-end logic. It could include code written in Python that handles server-side operations such as processing user requests, interacting with the database, and generating dynamic content to be rendered in the HTML templates. Model files. These are the model files which contain algorithm information which will be loaded into the project code during the runtime. IPYNB files. These are the Jupyter Notebook files which contain a combination of code, graphs, and outputs all in one place. It allows users to write and execute the code in individual cells, making it a popular choice for data science. Signup.db file. This file is a database file used to store the user information. Coming to the execution of the project, firstly, you need to copy the path of the code folder from the address bar of the file explorer. Then open Anaconda prompt. Use the command cd followed by a space and then paste the copied path. This command is used to change the current directory to the code folder's path. Now Compile the app.py file using the command python space app.py in the Anaconda prompt. This command will execute the Python script and perform a runtime check for any syntax errors or logical issues. After running the app.py file, the Flask framework will host the application locally at the default address with the port number of 5000. Copy the local link which is provided by the framework and paste it in any web browser. I prefer Chrome. So, the home page of the project should now be displayed in the browser. This is a front-end built using the Flask framework. In this page, we have home button and sign up button. Firstly, click on sign up button so that the create account form will be opened where you need to enter the details and create an account for user authentication like username, full name, mail ID, mobile number, and a strong password. Then click on sign up so that all the given details are stored in signup.db and login.html will be opened where you need to access the application with username and password. Then click on sign in so that the prediction page has been displayed. In this page, we have prediction button, graphs button, notebooks button, and sign out button. Firstly, click on prediction button. As we are doing classification and detection, both the things are displayed. So let us check one by one. First with classification. When you click on classification button, the AI powered retinal classification will be open where you need to upload the retinal fundus images for classification. This is a place where you need to upload your image. So click here to select an image. The image has been successfully uploaded. Then click on classify image so that the given image is pre-processed and the output is displayed as diabetic retinopathy is detected. The prediction, the confidence score is of 100%. And here we have the original image which we have uploaded. And here we have heat map analysis image. And the probability of class like diabetic retinopathy is of 100%. No diabetic retinopathy is of 0%. We also have the analysis details and recommendations for diabetic retinopathy. And more important safety measures are also there. Then click on analyze other image. Again, the upload form will be open where you need to select the image. The image has been successfully uploaded. Click on classify image so that the given input image is pre-processed and the output will be displayed as no diabetic retinopathy. The confidence score is of 100%. This is the image which we have uploaded and this is a heat map analysis. And we also have the class probabilities like DR 0% and no DR is 100%. And here we have the analysis details. Along with that, we have the recommendations and important safety measures. Now click on the detection part. When you click on the detection button, the AI powered retinal lesion detection will be open where you need to upload the retinal fundus images for detection purpose. This is a place where you need to upload the image. Now select the image. The image has been successfully uploaded. Click on detect lesions so that the given image is pre-processed and the output is detected as normal with the bounding boxes. And we have the detection information given below. And then click on detect other image. Again, the form will be opened. Select a random image. Click on detection lesion so that the given image is pre-processed and it's again given as normal image with along with the bounding boxes. And now click on detect another image. Select the image. The image has been successfully uploaded. Click on detect lesions so that abnormal has been detected with blue color bounding boxes. Then click on graphs so that classification and detection graphs are open. Let us check one by one. First, let us go with classification graphs. In this first, we have class performance graph. The bar chart compares the classification accuracy of different models. Most deep learning models achieve very high accuracy, close to 100, indicating strong performance. In contrast, SVM based approach shows much lower accuracy, around 0.5%. Overall, CNN-based and ensemble models clearly outperform traditional SVM methods in this task. Next, we have classification performance for precision score graph. Next, we have Class performance for precision score graph. This graph shows the precision scores of different classification models. Most deep learning and ensemble models achieve very high precision, meaning they make very few false positive predictions. However, SVM, RBF, and EffNet V2 plus SVM have much lower precisions compared to others. Overall, deep learning based models outperform SVM based approach in terms of precision. Next, we have recall graph. The graph compares recall scores of different classification models. Deep learning models like MobileNet V2, DenseNet 121, Exception, NASNet Large, and Ensemble achieves very high recall, meaning they correctly identify most positive cases. Traditional methods such as SVM, RBF, and EffNet V2 plus SVM perform slightly worse, around 0.5% of recall. Overall, CNN-based models and Ensemble clearly outperform SVM-based approach in recall. Next, we have F1 score graph. The graph shows the F1 score comparison of different classification models. Most deep learning models achieve near perfect to F1 score, indicating balanced precision and recall. In contrast, SVM, RBF, and EffNet V2 plus SVM perform much worse with F1 scores around 0.5%. Overall, CNN based on ensemble models significantly outperform traditional SVM approaches. Now let us check with detection graphs. In this, first we have YOLO precision graph. The graph compares the precision of different YOLO models. YOLO V5 achieves the highest precision, followed closely by YOLO V8. YOLO V9 and YOLO V11 shows lower precision, around 0.55% and 0.51% respectively. Overall, early YOLO versions perform better in precision in this comparison. Next, we have YOLO recall graph. The graph compares the recall performance of different YOLO models. YOLO V5 and YOLO V8 show similar recall, around 0.79% to 0.80%, indicating comparable detection coverage. YOLO V9 achieves the highest recall, meaning it misses the fewest objects. YOLO V11 is slightly lower than V9 but still perform better than V5 and V8, showing overall improvement in newer versions. Next, we have YOLO MAP graph. The graph shows the mean average precision of different YOLO models. YOLO V5 achieves the highest MAP, indicating the best overall detection accuracy. YOLO V8 and YOLO V9 showed the gradual decline in MAP, suggesting reduced precision recall balance. YOLO V11 has the lowest MAP, indicating weaker overall detection performance compared to earlier versions. Then click on Sign Out. So finally, the EffNet SVM hybrid model effectively combines deep feature extraction and robust classification to accurately detect the classified diabetic retinopathy from retinal fundus images. By leveraging EffNet and SVM, the system improves diagnostic accuracy while reducing dependency or manual analysis. This approach provides a reliable and efficient solution for early stage of diabetic retinopathy detection and large scale screening. This is all about your project. Thank you.
Thank you for watching video. For more projects, please visit our website www.trueprojects.in. For updates on latest project videos, please visit True Projects YouTube channel and subscribe.